Right, we ready?
Yeah, I am actually.
Good job, Brett. Okay, so today we're learning about logarithms. Are you excited? It's a bit of an intimidating word, but it actually just means the inverse of the exponential function. Okay, and we've dealt with inverses already in the functions unit. We've looked at them in the transformations unit. And again, we get to look at them in the exponents and logarithms unit. So yesterday we explored what an exponential function looks like. The logarithm of that is just the inverse. Okay, so whatever the, actually I'll ask you guys, what do we know about inverses?
Just the x inverse.
Okay, good. So the x coordinate and the y coordinate switch. What about domain and range?
The range, just domain of the original.
Good. So domain and range ultimately switch as well. Because if the x values switch with the y, then the domain switches with the range. And then there's one more thing about inverses. It has to do with the transformation. What's that? What was that? Good, it reflects over the line y equals x. Okay, so you guys know all about inverses, which means you can do awesome with logarithms. Okay, so let's just take a look here. We're looking at the exponential function y equals 2 to the power of x. We have to find algebraically the inverse of that. So what do we do with the x and the y? All right, flip them. Good. Okay, so we get x equals 2 to the power of y. No offense, yesterday you two weren't here. We just cruised through. We had a great class. Okay, you were here. You weren't. And now you're talking and you're distracting me. Can we still have a great class with you?
I sure hope so.
I sure hope so too. Thanks. Okay, so we just switched the x and the y. Sorry, Jackson. Okay, we just switched the x and the y. Now, how are we going to get this into a y equals equation? So normally with inverses, we switch the x and the y, and then we have to rearrange for y equals. Can you guys think of any way that we can get the equation to be a y equals? So the y root. Are you going to take the y root?
You have to log it.
You got it. Okay, we're going to have to use logarithms. Okay, and basically, this says a logarithm will look like log base 2 of x equals y.
No.
Now do I have a y equals? Magic. But we're going to get into a little bit of what the logarithm is first before we start using the notation. Okay, yesterday we looked at the graph of y equals 2 to the power of x. And what we could do is we could input all these values into both equations to get the table of values to then plot the points. Or you could just fast forward a little bit. So go to the next page. And it's pretty much repeated again on the next page. So let's just do it once. We're going to go back to the top of the page in a bit, but just hold your horses. So first let's review the exponential function. This is review from yesterday. Okay, do you remember if our base is a number greater than 1, is it a rise or a fall? It's a growth. Good. Okay, so it's going to rise. And what was the y-intercept? If you can't remember, okay, some do.
Equals A.
Okay, our a is 1 in this case. Our b is 2, and we're going to the power of x. If we're finding the y-intercept, what does x equal? 0. Good. So y equals 1 times 2 to the power of 0. And anything to the power of 0 is? 1. Good. So y equals 1. We found our y-intercept. It's going to be 1. And on your page, it's giving you kind of a hint of the shape of what an exponential function looks like. Okay, see that arrow at the bottom? You're going to go through the y-intercept and connect to the other arrow. That's the shape of an exponential function. This one is growing sharply. So let's just review some of the features of an exponential function where b is greater than 1. Okay, what's the domain?
Oh, yeah.
Okay, x is going forever to the left, forever to the right. right. So we have x as an element of all real numbers. Do we have any asymptotes that are basically guiding the line, the graph? A line that this exponential function is approaching? Okay, if we look, it's approaching y equals 0, or the x-axis. So we could call that our horizontal asymptote at y equals 0. And if this graph is not going to touch the x-axis, what is our range? Y is greater than 0. Perfect. Do we have an x-intercept if it never touches the x-axis? Nope. And what's your y-intercept?
1.
Well, we already figured that out. It's 1. Okay, and I'm going to put the ordered pair 0, 1. So now we talk about logarithms. The logarithm is the inverse of an exponential function. And you guys already told me it's the reflection across the line y equals x. So if we're reflecting over this line, and if the x and the y coordinates change, if our y-intercept originally was 0, 1, what's our new y-intercept going to be? 1, 0. And is it going to be a y-intercept? X-intercept, because now y is 0, right? So our new x-intercept is 1, 0. So why don't we mark that on the graph? If we were to switch all the x and y coordinates, okay, mirroring across this line, okay, this arrow's kind of shooting out, shoot out this way. So you're reflecting across the line y equals x. Here they're describing this graph as x equals 2 to the power of y, but I also want you guys to write log 2 of argument x equals y.
Did you say argument?
Yeah, we're going to have an argument. Now I'll go through the notation in one moment. If we look at the logarithm function, or the inverse function, what is the domain? Remember inverse, the domain and range do what? Switch. So the range of the original exponential function was y is greater than 0. So what is the domain? X is greater than 0. And let's take a look at the graph too. Here's our y-axis. Okay. The logarithm is approaching that y-axis, but it's never going to touch it, it's never going to cross it. So it's everything to the right, which means x is greater than 0. Okay, the range is going forever up, forever down. Okay, so that's y is an element of all real numbers. If it's approaching the y-axis and not touching the y-axis, will we ever have a y-intercept? Nope. And we will have an asymptote. It's now going to be a vertical asymptote, and the logarithm function is going to be approaching the line x equals 0. X equals 0 is the equation of the y-axis. So now that we've seen what it looks like, I just want you guys to go back to the top of the page, and we're going to read through the definition of a log. Okay, so once again, a logarithm is the inverse of the exponential function. We've already gone through how we would write the logarithm, but if we started with the inverse, x equals 2 to the power of y, the whole point of it was we couldn't figure out what y equals, so we're going to set y equal to the logarithm of base 2 to the argument x. Okay? One thing that we're going to note is in the exponential equation we have base 2, in the logarithm we also have base 2, so the base will never change. Okay, the exponent that we're solving for is now the value that we're solving for. Okay, so we can figure it out. Okay, and then the argument will now be what's beside the base. we're going to go through a lot of practice of switching between exponential and logarithm notation, and hopefully you'll get the idea. Okay, so you're wondering where this argument business came out of? Okay, well, Booker, here it is. Okay, so we have our b is the base, x is your argument, and y is the value that we're going to be searching for. So let's just explore a little bit more the relationship between an exponential function and a logarithmic function. Okay, so we have two tables of values, one for y equals 2 to the power of x, and one for the logarithm base 2 argument x. Okay, given a bunch of x values and corresponding y values. In the first little note here, we have 0.38 on the graph y equals 2 to the power of x. So let's just mark that up. So on the graph y equals 2 to the power of x, we have x is 3, y is 8. Subbing the x and the y into that equation, okay, the y is the 8, the x is the 3, we get 8 is equal to 2 to the power of 3. Do you guys agree? 2 cubed is equal to 8? Now we're going to go to the table of values for the 0.83, which is our x and y coordinate, from the logarithm. If we plug in the 8 for our x and the 3 for our y, we get this. 3 is equal to log base 2 argument 8. These two things are basically equivalent. So this is exponential form, this is log form. So we'll use this point, we'll practice. Okay? So what statement can be made from this point on the graph y equals 2 to the power of x? So this is your x and this is your y. We're just going to sub xy into that equation. So our x is -2, which means we have 2 to the power of -2. And our y is 1/4. Is it true 2 to the power of -2 is 1/4? If I were to rewrite this, it'd be like 1/2 squared, right? Which equals 1/4. Okay, next one we have the 0.164. We're going to sub that into the logarithm. Okay, again we have our xy. We're going to replace xy into this log. So y is equal to 4, and our x was equal to 16. Just practicing going from log form to exponential form. I'm just going to walk you guys through it. You always take your base, it's going to be the exact same base for your exponent. So the base of the log is the same base for the exponent. You're always going to raise it to whatever the log equals. So 2 to the power of 4. And that will equal the argument, which is 16. Do you guys agree 2 to the power of 4 is equal to 16? Okay, now what if I got confused and I was like, okay, well I know the base is 2, okay, I remembered that part. Do I put this 16 here? And then that equals 4? Does that make sense? Does 2 to the power of 16 equals 4? No. So you just kind of have to think about it, and if, when in doubt, evaluate, and if it doesn't work out, then you know you got your numbers mixed up. So that's wrong. Okay, so we're just going to practice going from log function or log form to exponential form on the bottom table, okay? Now technically we could use the table of values from above. Actually, we'll need a little bit of reference for that. Okay, so the first example they gave was log base 2 of argument 8 equals 3. And in exponential form, they're saying that 2 to the power of 3 equals 8. Okay, 2 to the power of 3 equals 8. In this one, just keep in mind that the equation for the log form was y equals log, what was it, 2 and then x. Maybe I'll write it the other way so it's the same. 8 log 2x equals y. So in the table above, our logarithm has base 2, And then we're looking for the points x and y. So in this case, they gave us x was 8. If you look at the table, when x is 8, y is 3, right? So x is 8, y is 3. Here we're doing log base 2. When x is 4, what's your y? 2. And we're going to convert that to exponential form now. So you're going to take your base 2, raise it to what it equals, and that will equal your argument. Do we agree 2 to the power of 2 is 4? Next one, let's look on our table of values again. So when x is 2, y is 1. So if I were to convert that to exponential form, use your base 2 to the power of your exponent, 1, and that will equal your argument. 2 to the power 1, is that 2? Yep. And lastly, when x is equal to 1, y is equal to 0. So we take our base 2, raise it to the y value, and we should get our argument. Anything raised to the power of 0 is 1. So that's going from logarithmic form to exponential form. We're going to do the opposite now. We're going to go from exponential form to logarithmic form. So looking at this first example, we have 2 to the power of negative 3 is equal to 1/8. Okay? Another way that we could just, for this first one, solve is when we have 1/8, what's your y value in the table of values? Negative 3. Okay, converting, just looking here, 2 to the power of negative 3, does that equal 1/8? And I'll just go through. 2 to the power of negative 3 is the same as writing 1 divided by 2 to the power of positive 3. And when we evaluate that, we get 1/8. Okay, let's try this one. Okay, what's our base? 2. I just underlined it. Okay, what is the x value? Yeah.
So whenever the number besides log, it's always the base number?
Yeah, so this little number, subscript, is the base. Always going to be the base. Okay, so in this case, our base of the exponent is the base of the log. And whatever the exponent here is, that's going to be what it equals to. See how it equaled negative 3 and that was our exponent?
Yeah.
Okay, and then in the exponential form, whatever it equals to, that's called our argument. And that will be the argument in the log. And it just takes a bit of practice, figuring out where everything goes. Let's try the next one. What's your base? 2. Good. Okay. And what's it going to be equal to? Forget about the argument for now. Good. Always equal to your exponent. And then whatever's left over is your argument. So now that we've gotten the hang of it a little bit, we're going to try it with the exponential function or statement 10 to the power of 3 equals 1,000. So writing that in log form, who can tell me the base? 10. Good. So we have log base 10. Okay, what's our argument? Or what's it going to be equal to maybe? So it's going to be equal to 1,000? Okay. Let's just try this. If I were to reverse this, you go your base, what it's equal to, is that going to 10 to the power of 1,000? Is that going to equal negative 3? No, so we made a little mistake. Okay, we just had to switch places. It's going to be log base 10, argument 1,000 equals negative 3. Positive 3, I don't know where I got the negative, sorry. Okay, part B, we're going to change the log to an exponential statement. So we have log base 5 of 625 equals 4. Hannah, what's our base?
5.
To the power of what? Equals what? Good. Okay, and if you tested that out, 5 to the power of 4 should equal 625. This next little bit is basically just summarizing the characteristics of a logarithmic function. And we kind of already talked about it while we looked at the graph. So first of all, the x-intercept we found was 1. Maybe just to remind you guys. It looks like this. Okay, so the x-intercept was 1. There was no y-intercept. There was a vertical asymptote on the y-axis at x equals 0. The domain is x is greater than 0. And the range is all real numbers. Okay, and then we also looked at how this log form was equal to this exponential form. And the base will always be the same for both. So we're just going to carry on trying to convert from exponential to logarithmic form and logarithmic form to exponential form. Okay, so in the first one, they're telling us to state the inverse of the following functions, but then we need to answer in the form y equals. So if I were to take the inverse of this function, what would I do with the x and y? Switch them. Good. Okay, so now we have x equals log base 3 y. So the first step, switch x and y. Okay, and then the next step is we're going to have to put that into exponential form. And that's because we need to make it a y equals equation. So what's our base of this log? 3. What's it going to be raised to? X. And voila, it equals y. Okay, next one, we have to switch the x and y again, because we got to take the inverse. So we get x equals 8 to the power of y. And then we've got to go from exponential form to logarithmic form. So we know we need to have a y equals, and that's going to be your exponent. And that's going to be equal to log of the base 8 with argument x. Now we just get to fly through this. Practice, practice, practice. Okay, so we don't have to do the inverses anymore, but we do just have to convert. So we're going from logarithmic form to exponential form. So, Bruce, can you help me out with this one? What's your base?
7.
What's your exponent?
4.
And what will it equal?
X.
Good. Okay, so 7 to the power of 4 will equal x. And if you're ever asked to solve for a missing variable or an unknown variable, this is a way you can do it. If you didn't know what the argument was, you can put it into exponential form and now solve. 7 to the power of 4, Robo, equals x. Josie, how about the next one?
It's y, so.
What's your
5
base?
to the y
5 to the y, good.
equals 15.
Awesome. Hey, Emily.
T to the n equals 3.
He's got it. Now this next one is a little bit trickier because we have a coefficient in front of the log. So what you have to do first is divide the 4 on both sides. So you want to isolate the log. Divide by 4, divided by 4, and then we get 5 over 4 equals log base b 6. We still haven't converted it though. So now we need to convert to exponential form. So we take our base b, we raise it to the value 5 over 4, and that will equal the argument. Question? Sure? And now the flip. So instead of solving for exponential form, we're going to go from exponential form to logarithmic form. Okay, so we have log base 4 of 64 equals 3. So whatever your exponent is, that's always going to be the value that it equals. Might try writing this one opposite this time. So I'm going to start with what it equals. It always equals that exponent. So negative 3 will equal your log of the base given, so 2, and argument 1 over 8. Again, it will always be equal to that exponent. So d will equal log of your base, which is e, argument f. Always going to equal your exponent. So 5 will equal log base a 2x plus 4. Okay, and we're just going to finish with one calculation. Okay, so calculate the value of t if log base 2 argument x equals 3 and log base 2 argument t equals x. Okay, so first what we're going to do is we're going to put this into exponential form. Sorry, my marker's slowly dying. Okay, so by doing that, let's just see. So we have base 2. Maybe I'll get someone to help me. Brett? What's your base?
2.
Good. What's your exponent? Good. We have 2 cubed equals x. And when we evaluate that, we get 8 equals x. Now that we know that 8 equals x, we can sub this into the other log statement. Okay, so we have log base 2 argument t now equals 8, because we just solved that x equals 8. And again, we need to put this into exponential form. By doing that, we get 2 to the power of 8 equals t. And what's 2 to the power of 8? 256. You guys are on it. Good. So we're going to end there today. I think that's enough for one lesson.